Hello everyone! So today, here in Mechanics of Deformable Bodies, we are now going to discuss the second part of the discussion about the fundamental concept of stress. So for this topic, students must be able to design simple dimensions such as length, width, thickness, or diameter of materials based on the allowable stress of the material. Second, compute for the bearing stress, internal compressive force, or resisting area of the body. And lastly, compute for the maximum pressure that a thin-walled cylinder can safely withstand. So let's start our discussion. Before the discussion, you have to answer first the following pre-assessment. For number 1, the 1-inch pin at A is supported by 2 fixed leaves and the free body diagram of the center segment of the pin is shown in figure C. If F sub A is equal to 40 kips, determine the shear force BA and the shear stress in the pin. So this is the illustration for number 1. And for number 2, if AB has a normal stress of 13 megapascal and BC has a normal stress of 10 megapascal, determine the diameter in millimeters with 2 decimal places in each rod. So FAB is equal to 650 Newton and FBC is equal to 400 Newton. So for these questions, what you're going to do is comment in the comment section your name, your section, the number that you're answering, and the item that you're answering. And don't forget to include the unit of your answer. So maximum of 2 answers for every student. So the first students who will be able to comment the correct answers will receive the bonus point or bonus points. Okay, so I hope that you get the bonus point for this pre-assessment class. Let's discuss now the concept about allowable stress. So allowable stress, this is sometimes called working stress or design stress. So to properly design a structural member or mechanical element, it is necessary to restrict the stress in the material to a level that will be safe. So of course, that is the priority in the design, the safety. So to ensure this safety, it is therefore necessary to choose an allowable stress that restricts the applied load to one that is less than the load the member can fully support. So that is very important that in design, we are using an allowable stress instead of the actual stress. So allowable stress, take note of this, that it restricts that the applied load will be less than the load the member can fully support. Of course, in designing, we cannot apply a load to a structure wherein the strength of that structure cannot withstand that loading. So there are many reasons for doing this. For example, the load for which the member is designed may be different from the actual loadings placed on it. So as I've mentioned, instead of using the actual loadings in the design, we are going to use design loads or allowable loads. So there are so many factors that may not be accounted for in the design. That's why we are not going to use the actual loadings. So one of those is, let's say, the intended measurements of a structure or machine may not be exact due to errors in fabrication or in the assembly of its component parts. So that will have a significant effect in the strength of that structural member or mechanical element, right? So there are also some factors such as unknown vibrations, impact, or accidental loadings, and they can occur and they may not be accounted for in the design. Also, atmospheric corrosion, decay, or weathering tend to cause materials to deteriorate during service. And lastly, some materials such as wood, concrete, or fiber-reinforced composites can show high variability in mechanical properties. So that's why we cannot use the actual loadings. So again, we are going to use allowable loads instead of the actual load. So one method of specifying the allowable load for a member is to use a number called the factor of safety. So the factor of safety, or FS, so that's the acronym for that. That is the ratio of the failure load to the allowable load. So here, the failure load, so of course that is the load that when you apply to the structure will fail. So that failure load that is found from experimental testing of the material no, and the factor of safety is selected based on the experience, so that the above mentioned certainties are accounted for when the member is used under similar conditions of loading and geometry, no, as stated in mathematically, no, in the following formula. So the formula for the factor of safety is equal to the failure load over the allowable load. So again, the failure load, no, it can be found from testing, no, in the material, experimental testings of the material. So we can solve for the allowable load, no, by using this formula of the factor of safety. Okay. So of course, again, no, we are not going to use the load, no, that will cause the structure to fail. No, we are going to use allowable load in our design. No, so that's it. Okay, so if the load applied to the member is linearly related or directly proportional to the stress developed within the member, as in the case of using normal stress sigma is equal to P over A and shear stress tau is equal to V over A, then we can also express the factor of C as a ratio of the failure stress to the allowable stress. That is, factor of safety or Fs equal to the normal stress at failure over the normal stress or the allowable normal stress, or Fs equal to the shear stress at failure over the allowable shear stress. No? So in any of these equations, the factor of safety must be greater than 1 in order to avoid the potential for failure. So if the factor of safety is greater than 1, no, meaning to say the stresses, no, at failure, no, they are always greater than the allowable stress, right? So of course, if we design a structure, no, using the stresses at failure, no, or equal to that value or greater than to that value, the structure will fail, right? So that should not happen. No, that's why the allowable stresses, they should be less than, no, the stresses at failure, no. Ayan, so specific values depend on the types of materials to be used and the intended purpose of the structure or machine. For example, the factor of safety used in the design of aircraft or space vehicle components may be close to 1 in order to reduce the weight of the vehicle. Or in the case of a nuclear power plant, the factor of safety for some of its components may be as high as 3 due to uncertainties in loading or material behavior. No? In many cases, the factor of safety for a specific case can be found in design codes and engineering handbooks. So these values are intended to form a balance of ensuring public and environmental safety and providing a reasonable economic solution to design. Okay. So using allowable stresses, we can actually design simple connections. By making simplifying assumptions regarding the behavior of the material, the equations normal stress sigma is equal to P over A and shear stress tau is equal to V over A can often be used to analyze or design a simple connection or mechanical element. In particular, if a member is subjected to a normal force at a section, its required area at the section is determined from this formula. So the required area, or A, is equal to the normal force, no, at that section, P, over the allowable normal stress. No? On the other hand, if the section is subjected to a shear force, then the required area at the section is equal to the shear force V at that section over the allowable shear stress. No? So through this, no, we can solve for the area and then the let's say required diameter, required thickness, or anything that we need, no, in the design of that connection. Okay. Okay, so just to summarize the procedure no, for designing simple connections. So when solving problems using the normal and shear stress equations, a careful consideration should first be made as to choose the section over which the critical stress is acting. Once this section is determined, the member must then be designed to have a sufficient area at the section to resist the stress that acts on it. This area is determined using the following steps, no. So we are going to determine first, no, the section wherein the critical stress will act, no. So the critical stress, that will be the largest stress, no, that let's say material, no, can experience, no. So you are going to use that stress. So again, the critical stress will be the maximum stress. Okay, so um now, for our steps here, no, we are going to solve first for the internal loading, no. Let's say that is a shear force or a normal force. We have to solve first for those forces, no. So we have to section the member through the area and draw a free body diagram of a segment of the member. So the internal resultant force at the section is then determined using the equations of equilibrium. And then after we solve for the internal loading, we can now solve for the required area, no. So provided the allowable stress is known or can be determined, the required area needed to sustain the load at the section is then determined from this formula. So area, or the required area, is equal to the normal force P over the allowable normal stress, and required area is equal to the shear force V over the allowable shear stress. Okay. Okay, so let's start solving sample problems for this. So the control arm is subjected to the loading shown in the figure. Determine the required diameter of the steel pin at C if the allowable shear stress for the steel is 8 kSi. So we are going to design this steel pin at C. So this is the steel pin at C. We are going to determine its required diameter. So in order for us to compute the required diameter, we have to determine first the required area, no, and we are going to use the allowable shear stress, which is equal to 8 kSi, and we also need the internal loading. No, so in order for us to solve the internal loading, we have to solve first the reaction here at point C. So in order to solve that reaction, we are going to apply what you learned in statics of rigid bodies or engineering mechanics, no. So let's start solving this. So again, we are going to design the steel pin at C. So we are going to compute the required diameter. Okay, so for our solution, we have to solve first, no, for the reaction here at C. So for the reaction here at C, no, for the internal shear, okay, we have to solve this reaction. No? So since this is a pin, okay, so this is a pin, so there will be one vertical reaction, that will be Cy, and one horizontal reaction, and that will be Cx. So to solve this, we are going to use equilibrium equations, no, so we can sum up moment at C, no, and after we take moment at C, no, we can solve for FAB, no, and after we solve for FAB, no, we can sum up forces horizontal. So summing up forces horizontal, okay, so that will be, our assumption is 0 for forces directed to the right, no? So since we already solved for FAB, okay, solving for CX, no? So that's the unknown here. Okay, so this will be negative FAB minus CX plus, so there is also a horizontal component for this, so this will be 5 times 4 over 5 is equal to 0. And we are going to substitute what we solved for FAB to solve for CX. So this will be negative 3 minus CX plus 5 times 4 over 5 is equal to 0. So solving for CX, no, if we input that in our calculator, that will be negative 3 minus CX plus 5, 4 over 5 is equal to 0. So that will be negative 3 plus 5 times 4 over 5, no, we can transpose Cx to the other side and it will become positive. And the value for Cx, therefore, will be 1 kip. no? So that will be 1 kip. So that's the value of Cx. So we also have to solve for the value of Cy. For the value of Cy, now we are going to use summation of forces vertical. So our assumption here is positive for upward forces. So summing up upward forces here, so this will be Cy minus 3 minus the vertical component of this 5 kips inclined force, no? So its vertical component is 5 times 3 over 5. So we use the slope triangle here. So this will be equal to 0. And then solving for Cy, that will be 3. So we will transpose everything, no, since we are going to solve for Cy. So that will become 3 plus 5 times 3 over 5. So our y here will be 6 kips, no? So we already solved for the reactions, no, or the components of the reactions at C, at pin C. So we are going to solve the resultant, no, of that reaction. So this will just be um, equal to square root of Cx squared plus Cy squared, no? So we already have the value of Cx and Cy. So the reaction, or the resultant reaction at point C will be square root of 1 squared plus 6 squared. So that will be 6.0828 kip. So we are going to use this reaction, no, to solve for the internal shear force. Okay. Okay, so the reaction force, no, that we solve here at pin at C, no, so that will be equal to the force, no, that will be applied here at pin C, no, due to the forces here in this force system. Okay, so that force will be equal to 6.0828, no, so that will be applied to the pin. And as you can see here, no, in the figure, okay, so the pin is supported by these two leaves, no? So there will be a double shear here, no? So since there will be two areas that will have the potential to tear, no, or will wherein the shearing will happen. So it can happen here at this point and here at this area, no? So there will be a double shear here, and if you are going to solve for the shear force for each shear force, so using equilibrium equation, so that will just be half of this force, no? So our shearing force will be equal to half of the reaction force, which is equal to 6.0828 over 2, and that will be equal to 3.0414 kip. So this is the shear force that we will use, no, in our computation. Now, to solve for the required area, so there is a given allowable shear stress, right, in the problem. Okay, so we are going to use this computed internal loading, which is a shear force, no? So substituting this value, so the allowable shear stress given is 8 KSI, so that will be 8 kips per inches squared, and then the shear force here will be 3.0414 kips. So solving for the area, so the area here will be, so if you input that in your calculator, 3.0414 kips over 8 kips per inches squared, so that will be 0.38018. So the unit for the area here will be inches squared, since this is KSI, no? So this is inches squared. So what we are solving again is the required diameter. So this is just the required area. So to solve for the required diameter, as we know, the area, or the formula for area, is pi over 4 diameter squared, no? Or it can also be pi r squared, no, for area of a circle, since we know that this pin, the section or the cross-sectional area of this pin is a circle. So that's the area, or the formula for the area of a circle. So the value of area that we solve, we are going to substitute that here, and this will be equal to pi over 4 diameter squared. So solving for the diameter here, no, so this will just be 4 times 0.38018 over pi, and then we square root this, we get the square root of this value. So the diameter that we are looking for here is 0.69574 inches, no? So this is the diameter that we need, no, for the steel pin. Okay, so this is the required diameter. Okay, this is now the answer. Alright, so for sample problem number 2, The rigid bar AB shown in the figure is supported by a steel rod at AC. So this is a steel rod having a diameter of 20 millimeter and an aluminum block. So this is the aluminum block, no, having a cross-sectional area of 1,800 millimeters squared. So the 18 millimeter diameter pins at A and C are subjected to single shear. No? So if the failure stress for the steel and aluminum is equal to 600 MPa or megapascal and 70 MPa or megapascal respectively, and the failure shear stress for each pin is 900 megapascal, determine the largest load P that can be applied to the bar. Apply a factor of safety of 2. No? So the factor of safety is equal to 2. So again, we are going to solve the largest load P. No? So the largest load P, it will be the smallest value of P, no, that we can solve from the given failure stresses, no, or stresses at failure, no, and we have here the factor of safety, and we can solve for the allowable stress, no, allowable normal stress, no, for steel and aluminum. We can also solve for the allowable shear stress for the pin, no. So again, for the steel, no, we have here allowable normal stress. No, we can solve for that, no, using this stresses at failure and factor of safety. And for the aluminum, so the aluminum block is this, no, so there is also a normal stress here at failure for the aluminum block, and we can solve for the allowable normal stress for this aluminum block also. And then for the pin, so the pin here that we are talking about, no, is the pin here at A. No, so the pin here at A, there is a failure shear stress of 900 megapascal, and we can solve for its allowable shear stress, no, using the factor of safety here. Okay, so let's try solving this problem. Okay, so again, we are going to solve for the largest load P. No, so to start solving this, no, since the given in the problem are stresses at failure and factor of safety, we have to solve first for the allowable stress. So this is the stresses that we are going to use, no, in our computation. So solving for the allowable stresses, so for the first one, that is the allowable normal stress for the steel rod AC. So that will be equal to the normal stress at failure over the factor of safety, which are both given. So the given in the problem are 680 for the normal stress at failure, and the factor of safety here is 2. So solving for this will be 340 megapascal. Now for the allowable stress or normal stress for the aluminum block here, so this is the aluminum block. Okay, so this will be equal to the normal stress at failure over the factor of safety. So from the given in the problem, this will be equal to 70 over 2, and then the value for this will be 35 megapascal. Now for the allowable shear stress for the pins here at A and C, so they will have the same the same value, so they will have the same design, no. So it will be equal to the shear stress at failure over the factor of safety. So from the problem, that is 900 and the factor of safety is 2, and then this will be equal to 450 megapascal. So we are going to solve for the value of P using each allowable stress, no. So after we solve for the value of P using each allowable stress here, we are going to choose the smallest value of P. Now, so I will explain later on why the smallest value of P will be chosen. Okay, so in order for us to solve for the value of P, now we have to solve first this force system, no, or the force system that will be generated the figure, no? So we are going to draw the free body diagram of member AB. So this is member AB, and then this is supported by a steel rod here, pin here at A, no? So there will be a reaction here at this support, no? So the reaction here will be this FAC, and then this is also supported by aluminum block here at point B, no? So the member AB, it's just like leaning, no? So this will just be like a smooth surface, no? So the reaction here will also be a normal force, so we will name that normal force as FB. Okay, so in order for us to solve this free body diagram, no? So as you can see here, this is a parallel force system, right? So as you've learned in your statics of rigid bodies or engineering mechanics, we can only generate two equations here since this is a parallel force system. So it can be one summation of forces vertical or horizontal, but in this case, these are vertical forces. So one summation of forces vertical and one summation of moment at any point, no? Or you can also use two summation of moments, no? So in this case, no, we are going to use one summation of moment. So let's say summation of moment here at point B, so that will be equal to 0, and our assumption here is clockwise for, or positive for clockwise rotation. So this will be negative P times 1.25 plus FAC times 2, no? So that will be 0.75 plus 1.25. So this will be equal to 0. So this will now be the first equation. Now for the second equation, again, we can use summation of forces, summation of vertical forces here, or another moment equation. So in this case, we are going to use another moment equation. So we will sum up moments here at point A. So this will be equal to 0. And again, our assumption here is positive for clockwise rotations. So this will be negative FB times 2 plus P times 0.75. So this will be equal to 0. So this will serve our equation 2. So as you can see here, we have three unknowns here, and there are only three equations, right? So this will just be the relationship, or serve as the equations, no, reflecting the relationship of P and FAC and P and FB. Wherein FAC, as you can see here, so this will be the normal force, no, that this steel rod will also experience, right? So we are going to use that, no. And for the aluminum block, the normal force here will be FB, no. So we are going to use these allowable stresses, no. As we know, for stresses, no. So let's say for the stress here at steel rod, no, to solve that, no, that will be equal to the internal loading, which is the normal force. And if we are going to solve for the normal force, no, here at steel rod, no, we are going to use FAC, and that will be equal, just be equal to FAC if we are going to use equilibrium equation to solve that internal normal force, right? So so let's start solving this now, no. So we will now determine each value of P that creates the allowable stress in the rod, block, and pins respectively. So we will start with rod AC. Okay, so again, we will start solving this steel, the value of P for steel rod AC. So the allowable normal stress for the steel rod is 340 MPa. No, so we will use this formula. So the normal stress will be equal to the normal force, or the internal normal force, over the cross section of the steel rod. So the computed allowable normal stress for steel is again 340 MPa. So we will make it kilopascal. So kilopascal is kilonewton per meter squared, right? So to make this kilopascal megapascal, we will multiply 340 by 1000, no? So we just converted this, no, to kilonewton per meter squared. So we will multiply 340 by 1000, or 10 cubed, no. So you have to be very accurate, no, or consistent with the units here. So the unit here will be kilonewton per meter squared. So FAC here, no, again, this internal normal force, if we solve for the internal loading here, no, here at this steel rod, no, the internal normal force will just be equal to FAC. So that will be FAC over the cross-sectional area of the steel rod, AC. So since this is a steel rod, so this will have a circular cross section, no, so the area for a circle will be pi over 4 diameter squared. So in the problem, no, the given diameter is 20 mm, no, so we will convert it into meter since the unit that we use here is meter squared, right? So we have to convert millimeter to meter, so we will just divide that to 1000, right? So the diameter will be 0.02 meter, so we will just substitute that here, no, so we can now solve here for FAC. So FAC will be equal to, if you input that in your calculator, 340 times 10 cubed, okay, times pi over 4 times 0.02 squared. No, so that will be 34 pi or 106.81 kilonewton. So the unit here is kilonewton. You have to be accurate plus with the unit. So this is the FAC, no, or the allowable normal force, internal normal force, no, for the steel rod. Now, we are going to substitute this value, no, from the equation 1. No, from here, no, we will substitute FAC to this to this unknown, and then we can solve for P. No, so solving that, no, using equation 1 nga, so this will become negative P times, okay, so negative P times 1.25 plus FAC, which is 106.81 kilonewton, times 2 is equal to 0. So we can solve here for P. So the value of P here is 170.90 kilonewton. So this is the allowable load P that we can apply here at this member, no, wherein it will not exceed, no, the allowable normal stress for the steel, no. So this will be for the rod AC. So we will also solve for the value of load P, no, using or for the for the black aluminum block. So let's proceed. So we are now going to proceed to block B, no. So we are going to solve for the load P, no, using the allowable stress for the aluminum block. Okay, so the allowable stress for the aluminum block, so that will be equal to the internal force or normal force, no, internal normal force over the area of the, or the cross-section area of the aluminum block. Okay, so the allowable normal stress that we computed is 35 MPa. No, so we will make MPa as kilopascal. So kilopascal is kilonewton per meter squared. And then we will multiply this by 1000. Okay, so this is just equal to 35 kPa or MPa rather. So again, you have to be accurate and consistent with the units, okay, so that we will not be lost, no, in our computation. So the normal force or the internal normal force for block AB will be equal to the FB that we computed, no. So if we solve for the internal loading using equilibrium equation, so that will just be equal to the FB, no, that we computed. Okay, so we are going to use also the area na that is given. So the area, the cross-sectional area for the aluminum block here at point B in the problem is 1,800 millimeter squared, right? So you have to convert that millimeter squared to meter squared. So converting that, so that will be 0.0018 meter squared. So again, you have to be consistent with the unit. Since we use meter squared here, the area here should be meter squared. So you have to convert millimeter squared to meter squared. Okay, now solving for FB. So this will be, if we input in our calculator, 35 times 1000 or 10 cube, that will times 0.0018, that is 63 kilonewton. Okay, so this is the value of FB. Okay, now we are going to use equation 2. So in equation 2, no, that is negative FB times 2, right? So we will substitute that value here. So this will become negative 63 times 2 plus P times 0.75 is equal to 0. So we can now solve for the value of P. No, so this is with respect to the allowable stress for the block or the aluminum block. No, so solving for P, this will be equal to 168 kilonewton. So this is the allowable load P that we can apply here at member AB, no, and it will not exceed the allowable normal stress for this block. No, so this is the allowable load P. Now, lastly, we are going to solve for the load P, no, the load P, using the allowable stress for the pin A and C. So the allowable stress here is a shear stress. No, so for the allowable shear stress, so that will be equal to the internal shear stress, no, internal shear force over the area. So for the internal shear force, no, so if we are going to solve for the force here at this pin, so that will just be equal to the reaction that we solved, no, here for the steel rod, no. So that is actually FAC, right? So, and as you can see here, the connection for the pins, how it is connected, uh, or how it connected this member AB and this rod, no? So, this will just have a single shear, right? Since the shearing will just happen in between, no? In between this, so this is this is the member AB, this one, here at the left part, and then this at the right part, this is the steel rod. So the shearing will happen in between, no. So this will just have or develop a single shear. So meaning to say, the reaction force here at the steel rod AC, which is FAC, so that will, if we solve for the internal shear force here at pin, so that will just be equal to that. So the shear force at V will just be equal to FAC. Okay, and then for the allowable shear stress, no, for pin, so that will be 450 megapascal. So we will convert that to kilonewton per meter squared or kilopascal, no, by multiplying 1000 here. Okay, so this will be equal to FAC. And for the area of the pin, so the diameter of the pin is given, right? So the diameter of the pin is in the problem is actually 18, right? 18 millimeter. So we will convert that to meter since our unit here is meter. Okay, so again, we have to be consistent with the units. Okay, so 18 millimeters, so that will be equal to 0.018 meter. Okay, so solving for FAC here, FAC here will be 114.51 kilonewton. So again, using equation 1, now we can solve for the value of P by substituting FAC. So this will be negative P times 1.25 plus 114.51 times 2 is equal to 0. So solving for P here, so this will be 183.22 kilonewton. Okay, so from all this, no, we are going to, from all the values of P that we solve, no, so the largest load P that the member AB can carry, no, it should be the smallest value. Okay, so the explanation for this is, let's say the smallest value here is 168 kilonewton. So if this is the smallest value, so it passed the requirement that it should not exceed, no, the allowable normal stress for the aluminum block, no. But if you are going to apply this, no, or use this force P, let's say to the allowable shear stress, no, for pin at A or C, no. So if you're going to use P here, no, P here, what will happen to this FAC? No, so if we use 168, let's say here, no, so since the value of P here is it is less than, no, than this value, no, so what will happen to this FAC, no, it will also be less, no, it will be lessened, no. So if the value of FAC will be less than this value, no, and we substitute that here, so what will happen here is that this allowable shear stress, no, for pins, no, it will not be exceeded since there will be a smaller value of FAC, right? So it will not be exceeded. On the other hand, if we are going to use, let's say, this value of P, no, so this value of P, it passed the requirement that it will not exceed, no, the allowable shear stress for pin. But if we are going to use this value of P, let's say to block B, no, and we substitute this P here, no, so this FB, so this FB, if the value of P here is will be greater, no, than this value of P, so this FB will also be greater, right? So it will increase, right? So this value of FB, if it will increase, no, or it will be greater than this value, no, so what will happen is that since this is greater value, this is greater, the FB here is greater, so it will exceed the allowable stress, no, or normal stress for the black or aluminum block, no. So meaning to say the aluminum block will fail, right? It will fail. So meaning to say we cannot use this force P or applied load P. We cannot use this, no. So instead, no, we are going to use the smallest, no. So the smallest P here is 168 kilonewton, no. So this is also smaller than the load P that we computed, no, using the allowable stress for the steel rod, right? So meaning to say, no, we are going to use 168 kilonewton. So 168 kilonewton, no, this will be the answer for this. Okay, so by comparison, as P reaches its smallest value, the allowable normal stress will first be developed in the aluminum block. Hence, the value of P here will be 168 kilonewton. So this will now be the answer. Okay? Okay, so we already discussed the first two types of stresses, which are the normal stress and shear stress. No? So we are now going to proceed to another type of stress, which is bearing stress. So if two bodies are pressed against each other, compressive forces are developed on the area of contact. So the pressure caused by these surface loads is called bearing stress. So it is also known as the contact pressure. Okay, so examples of bearing stress are the soil pressure beneath a pier and the contact pressure between a rivet and the side of its hole. So this is the most frequent problems, no, that we can encounter, no, in solving for bearing stress. So if the bearing stress is large enough, it can locally crush the material, which in turn can lead to more serious problems. So to reduce bearing stress, engineers sometimes employ bearing plates, so the purpose of which is to distribute the contact forces over a large area. Okay, so as an illustration of bearing stress, consider the lap joint formed by the two plates that are riveted together as shown in figure 1.12a. So let's say we have here these two plates, so this plate and this plate, and they are connected, no, by this rivet. Okay, so um, as we learned, no, so aside from the normal stress and the shearing stress that this plate and rivet will experience, no, so this system will also experience, no, what you call a bearing stress. No, as you know, if you are going to apply a load P, no, to this plate, no, towards this direction, so it will be pushed that way. So upon pushing this plate this way, no, so this rivet, no, so it will be stressed, no, at this side, because if you push the plate towards this way, so the plate will react, of course, no, and there will be a contact pressure between the rivet and the plate, no, in this area, right? So this is the part that will be most pressured, right, if we push this plate this way. So this area, no, so there will be a bearing stress in that area. So that area is this area. So the bearing stress caused by the rivet is not constant. So it actually varies from 0 at the sides of the hole to a maximum behind the rivet as illustrated in figure 1.12b. So again, if we are going to push this plate towards this direction, no, so this side of the hole, no, it will be pressured, no, by the rivets because of the contact of the rivet and the plate, no. So that pressure, no, that is called the contact pressure, no, and or also it can also be called as the bearing stress, no. So that stress, no, this is actually ano, no, very complicated because we know that at this side of the hole there will be no stress, right? So only this side will have a stress if you're going to push this plate this way, right? So this side, okay, also, no, at this point we know that the stress will be maximum, right? Compared to let's say the stress here at this side, it will be less. It will have a lesser stress at this point, no, compared to this point, no. So that will be ano, no, complicated if we compute the stress that way, no. So instead, no, to avoid that complication or complicated computation in the stress distribution, we are going to use the common practice, no, assuming that the bearing stress is uniformly distributed over a reduced area. So the reduced area is this area, ha. Okay, so this reduced area or the bearing area or the contact area, no, it will be taken as the projected area of the rivet. Also take note of this, class. Okay, so in reality, the hole, no, in the plate that is greater than the diameter of the rivet. Okay, so of course, how can you pass through the rivet, no, to the hole, no, if the diameter of the hole is equal to the diameter of the rivet? So the diameter of the hole, it should be greater than the diameter of the rivet so that we can pass through the rivet, right? But here, no, we are going to assume that the hole, no, is just equal, or the diameter of the hole is just equal to the diameter of the rivet. Okay, so the projected area of the rivet or the hole, no, so the projected area will be this area, this shaded area. So this is the diameter. Okay, this is the diameter and this is the area. So this is the contact area or the reduced area that we are going to use in the computation of the bearing stress. Okay, so that will be again, the reduced area AB. No, so that will just be equal to the diameter of the rivet or the hole times the thickness of the plate. So that will be the bearing area or the contact area or the projected area. Ha. So we are going to use this. No, so since bearing stress is just similar to normal stress, so normal stress that is equal to normal force over area, right? So here the area that we are going to use for bearing stress is this area. Okay, so where T is the thickness of the plate and D represents the diameter of the rivet as shown in the free body diagram of the upper plate in figure 1.12C. So this is that figure, no? So from this FBD, we see that the bearing force PB, no, so equals the applied load P, so that the bearing stress becomes so this is the ano, ha, this is the formula for bearing stress. So the notation is sigma sub B. So as I've mentioned nga, this is just similar to normal stress. So this will be equal to the internal bearing force PB, no, over the area or the bearing area. Okay, so here if we are going to solve for the internal bearing force PB, no, so using equilibrium equation, we can see here that that bearing force is just equal to P. So PB will just be equal to P, and then the bearing area, no, the bearing area will just be equal, no, to the contact area or the projected area nga, no, of the contact area between the rivet and the plate, no. So the bearing area will be equal to thickness of the plate and then the diameter of rivet. Okay, so the contact area AB, no, again, that is perpendicular to the, as I've mentioned nga, this is similar to normal force. So that is, the concept for this will just be the same. That the contact area AB is perpendicular to the internal compressive force PB, or the bearing force PB, acting in the separate bodies that are in contact with each other. So take note of this. In solving for the bearing stress, no, so that will be equal to the internal bearing force over the contact area. Okay, contact area. Okay, so we will now try solving problems for this topic. Okay, so for sample problem number 1, in the figure, assume that a 20 millimeter diameter rivet joins the plates that are each 110 millimeter wide. So these are the plate. So this is the two plates, no, and they are riveted here. And this rivet is 20 millimeter. Okay, and the plates are 110 millimeter wide. So the allowable stresses are 120 MPa for bearing in the plate material and 60 MPa for shearing of rivet. So determine the minimum thickness of each plate and the largest average tensile stress in the plates. Okay, so let's try solving this problem. Okay, so what we're going to solve here are the minimum thickness of each plate and the largest average tensile stress or normal stress in the plate. So to solve this, no, we are going to use, no, the allowable stresses given in the problem. Okay, so to solve this, no, so for the first one, we are going to solve for the minimum thickness of each plate. So we are going to use the allowable shearing for rivet given in the problem. So the formula for shear stress, as we know, that will just be equal to the shear force over the area of the rivet, okay, or the cross-sectional area of the rivet. So the given allowable shear stress, no, for the rivet is 60 megapascal, right? So we can also rewrite megapascal as Newton per millimeter squared. So that will be equal to the internal shear force, wherein the internal shear force here, no, when we solve that, no, using equilibrium equation, so the shear force V here will just be equal to P, okay, over the cross-sectional area of the rivet. So the cross-sectional area of the rivet is so rivet is has a circular cross-section, right? So the area of a circle is pi over 4 diameter squared. So the diameter given is 20 millimeters. So this will be okay since our unit here is millimeter also. So this can also be millimeter here. So we can solve here the allowable force P. So the allowable force P will be equal to 18,849.56 Newton. So the unit here is Newton since we made it Newton per millimeter squared. No? So this will be Newton. Now we will use this allowable force, no, for the bearing of plate material. No, so the allowable bearing stress, no, for the plate that is given in the problem, and for its formula, it will be equal to the compressive force or the bearing force PB over AB, or AB here is the contact area. No, okay. So in this case, the given bearing stress of the plate is 120 megapascal, or we can rewrite that as Newton per millimeter squared. So this will be equal to our PB here, or the bearing force here. Now, if we are, of course, the bearing will happen. Now, let's say for this upper plate, now if this plate is pushed towards this direction, again, this side, no, it will be stress. No, so the bearing force, no, that will cause the bearing pressure here, no, it will be just equal to P, right? Since if we solve that using equilibrium equation, we can see that PB will just be equal to P, right? So we will use the P that we solve here, which is 18,849.56 Newton. Okay, so we substitute that here. And then our bearing area here will be the projected area. So the projected area of the rivet here will be the diameter of the rivet, which is 20 millimeter, and the thickness of the plate. So this is what we are solving here, the thickness of the plate. So we can solve for the thickness of the plate here, since this is the only unknown here, right? So solving for this will just be 18,849.56, no? Divided by 120 times 20. So the thickness will be 7.85 millimeters. So the unit here is millimeter. You have to be consistent with the unit clause. Okay, so that will be millimeter here. So this is the minimum thickness, no, for each plate. No, this is the required thickness. Okay, so now we are going to solve for the largest tensile stress, no, or the normal stress, no, in the plate. So here, to solve for the largest normal stress on the plate, no, we will analyze here, no, where will be the critical stress, no. So the critical stress, it should be the largest stress, no, it should be the largest stress that the plate, no, will experience, no. So where will the area, no, where will the area where will be the critical area here, no, in solving for the normal stress. So the critical area here, no, so again, this is the formula for the normal stress, no, so that will just be equal to P over A. So in order for us to have the maximum stress, no, the area here should be the minimum, no, or the least area, no. So here, the least area, or the critical area, no, will be the area, no, at this section, right? So for let's say for this section, no, and then we solve for the normal stress at this section of the plate, let's say, no. So we know that the width of the plate is 110 times the thickness. The thickness is this given, or the computed thickness, no. So uh, so that will be ano, no, the normal stress at this section. But if we are going to solve for the normal stress, no, at the section of the plate here, no, if we pass a section through this part, no, of the plate, no, this hole will be subtracted, right, from the width of this of this plate, no. And if it is subtracted, it will give us a minimum area, right? So that will be the minimum area, or the least area, no, the lowest value of area that we can have to solve for the normal stress. So we will choose that. We will choose this section to solve for the critical stress, because if the area here will be lesser, no, than the area at this part of the plate, no, meaning to say that the stress here will be critical, no, at this section. So we will use the area at this section. So the area for this section will be 110 minus the whole. So the whole here is 20 millimeter, no. So we will subtract that, no, and then multiplied by the thickness of the plate, which is 7.85 millimeter. And then the internal normal force here, no, if you are going to solve for the internal normal force, so that will just be equal to the P that we solve. No, so the P that we solve is 18,849.56 Newton. So this is Newton, and then the area here is millimeter squared, no? Since this is millimeter, this is millimeter. Okay, so the stress here will be 26.68 Newton per millimeter squared or megapascal. So this will now be the largest average tensile stress in the plate. So this will now be the answer for item B. Okay, so this will now be the answers for this problem. Okay, so for sample problem number 2, the lap joint shown in the figure is fastened by 4 rivets of 3/4-inch diameter. So find the maximum load P that can be applied if the working stresses or the allowable stresses are 14 kSI for shear in the rivet and 18 kSI for bearing in the plate. So assume that the applied load is distributed evenly among the 4 rivets and neglect friction between the plates. So what we're going to solve here, class, okay, is the maximum load P. So the maximum load P will be the load P, okay, that will pass both criteria for shear and bearing. Now, so let's start solving this problem, class. Okay, so to solve this, we are going to use the working stresses or allowable stresses given in the problem. So let's start with the allowable shear stress. So we will design the rivet, no, using the allowable shear stress. So the allowable shear stress, no, that is a shear stress. So its formula will be equal to V over A, or the shear stress over the area of shearing. Okay, so the given allowable stress for shear, no, at the rivets is 14,000 KSI, so, or 14 KSI, so that will be equal to 14,000 PSI. So this will be 14,000 PSI, or pound per inches squared. So this will be equal to the shear force. So the internal shear force here for the rivets, no, so if you're going to consider, let's say, this lower plate, no, so this is the free body diagram of the lower plate. So there will be a shearing, no, on the 4 rivets here. So the 4 rivets here will have shearing forces. Okay, and if you are going to solve for the shear force V, no, using equilibrium equation, so that will just be uh, like 4V minus P, no, is equal to 0. So solving for V, or the shear force, that will be P over 4. No, so the shear force here will be P over 4, and then the area of the rivet will be pi over 4 diameter squared. So the diameter of the rivet is 3/4 inch. No, so since this is PSI, so inches squared, no, so the unit here should be inches also. So we can directly use the given, which is it is already in inch, no, so this will be 3/4 inch and then squared, no. So from here we can solve the value of P. So the value of P here is 24,740.04. So the unit for this will be the unit that we use here, which is pound, no, so this will be pound. So this is the load P, no. If you are going to use the criteria for shear stress in the rivets. Now, we also have to compute for the value of P using the criteria for the bearing, no, in the plate. Okay, so for the allowable bearing stress, no, so the given, it is given in the problem, no, and the formula for bearing stress is equal to the bearing force, or the compressive force, no, over the contact area, or the projected area, since this is for rivets, no. So the projected area is TD of the of the rivet, no. So that will be thickness of the plate times the diameter of the rivet. So for the bearing force, no, so each hole here, no, each hole of the plate, no, they will all have bearing bearing force, right, that will cause the bearing stress. No, so just like the shear force here, no, if you're going to solve for the bearing forces, no, um, using equilibrium equation, so that will just be 4 pb, no, minus p is equal to 0. So solving for pb, that will just be p over 4. No, so just like the bearing or the shear force, no, the bearing force will just be the same. So that will be p over 4. Okay, so substituting that here, so the given bearing stress, no, for plate is 18 kSI. So that will just be 18,000 PSI or pound per inches squared. And that will be equal to our bearing force will be P over 4. And then our thickness, no, the thickness of the plate is 7 over 8 inches. No, so that is also given. And then the diameter of the rivet is 3/4 inch. No, so again, you have to be consistent with the units. You have to check that. Okay, so we can solve here for P. So solving for P here, okay, so it will just be P is equal to 47,250 pound. No, so that is the value of P here. Now we are going to compare the values of P that we solve. No, so for shearing stress in rivets, no, the allowable load P or force P is 24,740.04 pound, while for the bearing stress criteria or criterion, no, so the allowable force P is 47,250 pounds. So this force P, this is less than this force, no. So the force P that we're going to choose here will be the minimum force P, no, because yun nga, as I've explained to you, no, in our discussion about allowable stress. So if you're going to use this P, no, of course for shear stress it already passed that criteria, no, for shear stress in rivets. And if you're going to use this for the bearing stress in plate, no, let's say we use that here here in this P here. Okay, so the value here is less than, no, compared to this P, no. So meaning to say the bearing stress will also be less than. So it will not exceed the allowable stress. So that will be okay. Okay, so we will use that, ha. So the answer for this, no, the largest safe load P, no, that the plate and the rivet can carry, no, or can be applied to the lap joint will be 24,740.04 pound. No, so this will now be the answer. So with the shear stress in the rivets being the governing design criterion. Okay. Okay, now let's proceed to sample problem number 3. In the clevis shown in figure 111b, find the minimum bolt diameter and the minimum thickness of each yoke that will support a load P, which is equal to 14 kips, without exceeding a shearing stress of 12 kSI and a bearing stress of 20 kSI. So let's solve this problem. So what we're going to solve here are the bolt diameter and the thickness of each yoke. So the problem here is that we have here a clevis, right? So this is the clevis. No, so if you're going to define a clevis is a U-shaped fastening device with two holes at the end. So two holes at the end for a pin or bolt to pass through. So this is the bolt. No, so this is the bolt here that is being passed through here. Okay, so the yoke in the clevis, no, so this part and this part, these are the yoke. No, these are the yoke of the clevis. Okay, so again, we are going to solve for the bolt diameter. So this is the bolt, no? This is the bolt that is passed through this clevis. Okay, and we're going to solve for the minimum thickness of each yoke. So this is the yoke, ha? This is the yoke. Okay, so this is the yoke. This is the yoke. Okay, so the thickness of the yoke is actually this thickness, right? So this is that thickness. Okay, anyway, so To solve this, no, we are going to use the allowable stresses, no, given in the problem. So, for the shearing of rivets, no, so for the shearing of rivets, the rivets are bolt, no, so the shear allowable shear stress is given in the problem, and the formula for shear stress equal to shear force over the shearing area. So for the shear force here, as you can see here, if you are going to apply load P here and load P here, no, so this bolt, no, it will have a double shear because the tendency here is that it will be torn at this part and at this part. No, so there will be a double shear here. No, so the shear force here, no, if you are going to solve for the internal shear force using equilibrium equation, that will just be 2V is equal to P, or 2V minus P is equal to 0. Right? So solving for V, that will be P over 2. So the shear force here will be P over 2. Okay, now for the allowable shear stress, that is 12 KSI, no, so that is kips per inches squared. So that will be equal to our P here, no, P over 2, the given or the allowable load P here is actually 14, right? So that will be 14, no, and our 2 here, we just bring that down here, no, so that will just be okay. And then the area here is the area of the cross-sectional area of the rivet or the bolt, no. So the diameter here is what we are solving, no, so that is unknown. So the area is pi over 4 diameter squared, no. So we can solve the diameter here, no, so since that is the only unknown, so to solve for the diameter, that will just be 14 over 12 times 2 times pi over 4, and then we just square root the answer for that since this is d squared. Right, so the diameter here is 0.86181, and the unit here, ha, is inches, since the unit here is inches, ha. Okay, so this is the diameter that we are looking for, no? So this is the minimum bolt diameter. Now, for the minimum thickness of each yoke, we are going to use the bearing, no, or the allowable bearing stress for the yoke. So the allowable bearing stress, no, so it is a bearing stress. So the formula is the bearing force, or PB, over the bearing area. Okay, now the given allowable stress, no, so that is given in the problem, and then for the PB, so the PB here, or the bearing force here, it will be here, no, at the yoke. So both yoke will have a bearing force each, no. So solving for the bearing force, no, using equilibrium equation, so that will be PB, or 2PB minus P is equal to 0. So solving for PB, that will be P over 2. So our PB here will just be P over 2, no, just like the shearing force here, no. But here the again, the bearing force is P over 2 also, over the bearing area, which is the projected area of the bolt, no, of the bolt. So the projected area of the bolt, no, will be this. So this will be the project. So the contact area will be here, right, at this side, no, since it will be pushed here. And so there will be a contact pressure here between the bolt and this yoke, no. So the projected area will be the diameter of the bolt times the thickness of the yoke, right? So that will be D times T, no. So substituting the allowable stress, no, or bearing stress in the problem, that is 20 KSI, or kips per inches squared. So that will be equal to again, P over 2. So the allowable force P is 14 kips, and then we just bring down 2 here, no, at the denominator. And then the diameter of the bolt, no, we already solved that. That is 0.86181 inch. And then the thickness is the unknown here, no. So we can solve for the thickness here. So that will just be uh, that will just be uh, solving for the thickness 14 over 20 times 2 times 0.86181. Okay. So the thickness here will be 0.40612 inches. So this will now be the answer for the minimum thickness of each yoke. So this will now be the answers for this problem. The diameter or the minimum bolt diameter is 0.86181 inch, and the minimum thickness of the yoke is 0.40612 inches or inch. Okay, so let's solve now sample problem number 4. A timber column carries a load of 100 kilonewton as shown in the figure. A concrete pedestal with bearing steel plate supports the timber column. Determine the bearing stress on the pedestal. Okay, so the timber column, okay, this is the timber column. Timber, so that is a wood. Okay, so these are the properties of the wood. So the diameter, so this since the given here is a diameter, meaning the wood has a circular cross section. Okay, so the diameter is 500 millimeter. The height, so this height is 3.75 meter. And the density is equal to 900 kilogram per meter cube. Now, we also have here a concrete pedestal. So the concrete pedestal is this one, no? So this is the concrete pedestal. So the given here is 750 by 750 millimeters. So that is the cross-sectional area of the pedestal. So meaning to say the pedestal, the concrete pedestal, this is a square, right? So its thickness, so the thickness here is this height also. So that is 700 millimeter. Okay, so this is just a little bit exage, no? So this is just 700 millimeter, no? This thickness of the uh, concrete pedestal. Now, we also have here a bearing steel plate. So the bearing steel plate is this steel plate, no? So the bearing steel plate, no? So that is 750 by 750 millimeters. So the cross section of this steel plate or bearing plate, this is also a square, no? And then the thickness, so this thickness is 100 millimeter, and then the density is 800 kilogram per meter cube. So the density for the concrete is 2,320 kilogram per meter cube. So what we're going to solve here is the bearing stress on the pedestal. So meaning to say the bearing stress on the concrete, this concrete, no? So to solve for the bearing stress here, no, we have to solve for the bearing force, no, and the bearing area, no. So let's solve this problem. Okay, so again, to solve for the bearing stress on the concrete pedestal, now we have to solve first for the bearing force or the compressive force, no, that we will have here in the concrete, no. So we are going to solve for this force piece because this will be the bearing force here, no. So here to solve for this P, no, we have to include the weight of the wood. So the weight of the wood, no, it can be computed, no, and also the weight also of the bearing steel plate, no. We can also solve for the weight of that, no. So using this formula, so this formula is for weight, no. So this is W is equal to rho times G times V, wherein W here, that is the weight, and then rho here is the density, and then G here is the gravitational acceleration, which is 9.81 meter per second squared for in metric system, no. So this is in metric system naman, so we will use that. And V is the volume, no, the volume of the material. So we can solve first for or we will solve first for the weight of the wood using this formula. So for the weight of the wood, that will be the density. So the density of the wood is 900 kilogram per meter cube, and then the gravitational acceleration, that is 9.81 meter per second squared, no. And then the volume of the wood, again, the wood is a circular, has a cross section, circular cross section, no? So the volume of this wood will be the area of the cross section times the height. So the area of the cross section is pi over 4 diameter squared, no? So the diameter here, no, so we have to be consistent with our units. So the units here are meter, no? So the diameter, it should be in meter. So the given diameter here is millimeter, so you have to convert that first to meter. So that will be 0.50 meters. So again, pi over 4 diameter squared, no, times the height of the wood, which is 3.75 meters. Now, so solving for the weight of the wood, that will be 6,500.89 newton. So the unit here is newton, ha, since this will be meter squared times meter, no, so that will be meter cube, and here meter cube will be cancelled, and what will remain here is kilogram meter per second squared. And take note that kilogram times meter per second squared, that is newton, no? Okay, so that will be the weight of the wood. Now for the weight of the steel, so following the formula, again the raw for the steel is 8,000 kilogram per meter cube times G, which is 9.81 meter per second squared, times the volume of the steel. So the volume of the steel will be the area, or the area of the cross section of the steel, which is a square, no? So that is a square. So that will be the area of that, and then times the thickness to get the volume. So that will be 750 times 750. But since this is in millimeter, now we will convert 750 to meter. So that will be 0.75 meter times 0.75 meter times the thickness. So the thickness here is 100 millimeter. So that will be 0.1 meter. So we can now solve here for the weight of the steel. So this is the steel weight of steel, has, so this is just an error. So this is the weight of the steel, 4,414.5 newton. Okay, so from here, now we can solve for the bearing or the compressive force P, no, here in the concrete, no? So using summation of forces vertical, assuming upward forces as positive, so this will just be P minus 110 kilonewton. So this is in kilonewton, ha, this 110. So that is 110 kilonewton. And for the weight of the wood, it should also be in kilonewton. So the weight here of the wood is 6,500.89 newton. So it should be converted to kilonewton, and that is 6.50089 kilonewton. Same with the weight of the steel. So the weight of the steel is 4.4145 kilonewton, and that will be equal to 0. Okay, so solving for P, so this will be 120.92 kilonewton. So this will now be the bearing or the compressive force that we are going to use in the computation of the bearing stress. So for the formula of bearing stress, that is equal to the compressive force or bearing force PB over the contact area AB. So the contact area here, so the contact area here will be the contact between the steel plate or steel bearing plate and the concrete. So the contact area will be the since they are both 750 by 750 millimeter, right? The cross section. So that will be, no, that will be the contact area, 750 by 750. Okay, so again, our compressive force or bearing force here is 120.92 kilonewton, and the bearing area, so since it is in millimeter, no, we will convert it into meter, so it will become 0.75 meter times 0.75 meter. So the answer for this, no, if we input this in our calculator, okay, so let's input this in our calculator, 120.92 over 0.75 times 0.75, that will be 214.97. So this is kilonewton per meter squared or kilopascal. So this will now be the answer for this problem. Okay, so we will now start discussing the tangential or longitudinal stress in thin-walled vessel. Okay, so for the fundamentals of thin-walled cylinder, so these are some fundamental formulas that we are going to use. F is equal to mg small letter p is equal to F over A, rho is equal to M over V, and then F is equal to rho times GV. Okay, wherein F here is equal to force, small letter P, that is equal to pressure, A is equal to area, the rho is, that is the density, no, and then V is the volume, M is mass, and then G is acceleration due to gravity. So we are going to use these formulas for this topic. Okay, so there are two thin vessels that we are going to study in this topic. So they are cylindrical vessels and spherical vessels. So cylindrical or spherical vessels are commonly used in industry to serve as boilers or tanks. No, so when under pressure, the material of which they are made is subjected to a loading from all directions. So although this is the case, the vessel can be analyzed in a simple manner provided it has a thin wall. So in general, a thin wall refers to a vessel having an inner radius to wall thickness ratio of 10 or more. No, so again, no, so this is the ratio, no, so that we can say that the thickness of a vessel is a thin wall. No, so it should be R over T, and it should be greater than, no, or equal to 10, no. Okay, so specifically when R over T is equal to 10, the results of a thin wall analysis will predict a stress that is approximately 4% less than the actual maximum stress in the vessel. So for larger R over T ratios, this error will be smaller or will be even smaller. Okay, so cylindrical pressure vessels such as this gas tank have semi-spherical end caps rather than flat ones in order to reduce the stress in the tank. So we are going to um, uh, extract that conclusion, no, from this statement, no, in the discussion of this topic. Okay. Okay, so we will start our discussion with cylindrical vessel. So consider the cylindrical vessel in figure 8.1a. So this is that figure, no? So having a wall thickness T. So the wall thickness, so let's say this is the cylinder. So the wall thickness, so this is the thickness of the vessel. So this is T, no? And inner radius. So inner radius, of course, that is measured from the inner inner wall. So the inner wall is here, no, and the outer wall, okay, so that's the outer circle, no. So the inner wall is the inner circle. Okay, so the inner radius is measured from the inner wall. So that is denoted as R, no. So that is the inner radius R. And this vessel, this is subjected to a gauge pressure P that develop within the vessel by a contained gas. So of course, if you're going to fill a vessel with gas or with a liquid, no, so there will be a pressure caused by that contained gas or liquid. Okay, so due to this loading, a small element of the vessel that is sufficiently removed from the ends and oriented as shown in figure 8.1a is subjected to normal stress sigma 1 in the circumferential or tangential or hoop direction, or we call that circumferential or tangential stress, and then sigma 2 in the longitudinal or axial direction. So sigma 2, we call this as the longitudinal stress. Okay, so we can solve this stresses, these normal stresses, sigma 1 and sigma 2. Again, sigma 1, that is the circumferential or tangential stress, while sigma 2, that is the longitudinal stress. So we can get these stresses, no, by cutting the vessel. So let's say we cut the vessel this way. We cut let's say this is the vessel. So let's say we cut the vessel here, no, at this part, no, we section this vessel, no, we cut this vessel here. Okay, so what we will see here is this portion, right? So this will be the segment when we cut the vessel here, no, here at this section, no. So this will be the cut vessel. Okay, now this is actually, or this section or segment, no, we will have the sigma 1 here. or the circumferential or tangential stress. So this wall, no, so this wall, and this wall, no, it will be subjected to circumferential or tangential stress. Okay, so if you are going to just get a small strip, no, or a thin strip, no, from this cut segment, no, let's say we just consider this strip, no, so let's say the width of that strip is dy, but we can actually use also the entire length, no, of this vessel, no, but we can also use a segment only, no, so this width, no, let's say this is dy. Now this wall, no, this wall of this vessel and this wall, again, it will be subjected to sigma 1 or normal stress, or I mean tangential or circumferential stress. Okay, sigma 1 is circumferential or tangential stress, ha. So this stress, no, this is represented by this and this, no. So that's for the circumferential or tangential stress. Now, if we are going to cut the vessel here, so let's say we cut the vessel here, so we can see the segment this way, the cut section, right? So this will be that segment. So this wall, no, so this wall, as you can see here, this wall, it will be subjected to a longitudinal or longitudinal stress. Okay, so this sigma 2, so this represents the longitudinal stress that is experienced by this wall of the vessel. Okay, so these stresses, okay, they are caused, no, by the contained gas or the pressure due to the contained gas or liquid that is in the vessel. Okay, so let's solve this sigma 1 and sigma 2, no, in the next slide. So the hoop stress or tangential or circumferential stress, it can be determined by considering the vessel to be sectioned by planes A, B, and C, no? So that section, no, if we are going to get that segment, no, so this will be that segment. Okay, so a free body diagram of the back segment along with the contained gas is shown in figure 8.1b. So this is that figure. Here, only the loadings in the x direction are shown. So the x-axis here is, not this. So the x direction here, so these loadings, no, they are all in x direction. So these loadings are developed by the uniform hoop stress acting on the vessel's wall. So here in this wall and in this wall, there is an acting hoop stress or tangential stress or circumferential stress. So this is represented by this sigma 1 and sigma 1. Okay, so and the pressure acting on the vertical face of the gas. So this is the vertical face of the gas, and this is the this is the pressure. No, so this is the pressure, and this is denoted by small letter P. Okay, and this acts on the vertical face of the gas. Okay, so for equilibrium in the x direction, okay, so we will use equilibrium equation here. We will sum up forces horizontal is equal to 0 or Fx equal to 0. So here is the x direction. So all of these loadings are in x direction. Okay, so to solve for the forces here, okay, of course we have to convert first this sigma 1 into force. So sigma 1 is a stress, right? So to make it a force, no, we will multiply it by the area, okay, or the area perpendicular to it. No, so the area perpendicular to it will be dy and then t. Okay, so dy times t, that will be the area. So we will multiply that to sigma 1, okay, so that it will become force. No, so since we have here two sigma 1, sigma 1 here and sigma 1 here, we will multiply it by 2. Okay, and then since the pressure that is in opposite direction, so that will be minus. And then pressure is actually also like stress. No, this is just like force over area. So to convert this to become a force, no? So we will just multiply this pressure, no, by the area perpendicular to this. So the area perpendicular to this pressure is this area, no? So this is 2r times dy, right? So that's the area, no, perpendicular to the pressure, right? So again, that is 2r, or 2r because this is diameter, no? So diameter is 2r, right? So 2r times dy. Okay, so that will be equal to 0. So solving for rho 1 here, or sigma 1 rather, solving for sigma 1, which is the tangential or circumferential stress, no? So we can cancel out dy here. No, we can cancel out, and then what will happen here, it will become 2 will also be canceled, right? 2 will be canceled, so this will become pr over t, right? So to solve for sigma 1, or the tangential stress. So this will now be the tangential stress acting, okay, on the this wall of this ano no, segment of the vessel. Okay. Okay, so the longitudinal stress, it can be determined by considering the left portion of section B of the cylinder in figure 8.1a. As shown in figure 8.1c, so this is figure 8.1c, sigma 2, or the longitudinal stress, acts uniformly throughout the wall. So this is the ano no, cut segment, no, or cut section. So this is the segment. So this wall, okay, this wall of the vessel, this is subjected to longitudinal stress sigma 2. No, and it acts uniformly throughout the wall. And P, or the pressure P, so the pressure P, this is caused by the ano ha, the contained gas or liquid of the vessel. So its direction is this way. No, so if its direction is this way, okay, so the direction of the stress, it will be directed oppositely. Okay, so the stress will be directed this way. Okay, so this is ano ha, this represents sigma 2, or the longitudinal stress acting on the wall of the vessel. So since the mean radius, okay, or the average radius of the outer and inner radius is approximately equal to the inner radius, no? So we will use the inner radius, okay, of the vessel here. Now to solve for the sigma 2, okay, we will sum up forces with respect to y direction. So our y-axis here is here, okay? So this is the y-axis. So all of our loadings here are with respect, or directed, no, in the y-axis, okay? So we will sum up all the forces with respect to y-axis. So we have to convert this stress and pressure to force, no, in order to do that, okay? And this will be equal to 0. Okay, so let's first convert sigma 2 into force, no? So sigma 2, this is acting at the wall. Okay, so the area of this wall, we can solve that by solving the circumference of this inner circle, no, which is that is 2 pi r, right? That is 2 pi r, the circumference of the inner circle, times the thickness of the wall. Okay, so that will become sigma 2, or that is the longitudinal stress, times the area. So the area of this wall is 2 pi r times t. Okay, and then the pressure, since that is directed oppositely, it will be negative here. So pressure times the area, no, wherein the pressure acts. So the area wherein the pressure acts, it will be the area of the inner circle, no, or the inner wall, which is a circle, and that is pi r squared. So that will be pi r squared, so this will be equal to 0. So solving for sigma 2, or the longitudinal stress, we just transpose it on the other side and solve for sigma 2 by dividing both sides by 2 pi rt. Okay, so by doing that, pi will be cancelled, right? And then the r here, no, 1 r here will be cancelled, and then this r will be cancelled. Okay, so that sigma 2 will be equal to PR over 2t, right? PR over 2T. So this will now be the formula for longitudinal stress. And um, okay, so this will now be the formula. Okay, so for the formula of tangential and longitudinal stress, so these are the formula. So in the above equations, sigma 1 and sigma 2 are the normal stress in the hoop and longitudinal directions respectively. Each is assumed to be constant throughout the wall of the cylinder, and each subjects the material to tension. So they are both tension. So the stress here are tension, and also here tension, since they are pulling away, right, from the wall. Okay, so the small letter P here is the internal gauge pressure developed by the contained gas. And then the R here is the inner radius of the cylinder, and then the T here is the thickness of the wall. So if we are going to compare these two formulas, no, note that the hoop or circumferential or tangential stress is twice as large as the longitudinal or axial stress. No, so since this is this is over 2, so meaning to say sigma 1 is 2 times the longitudinal stress, right? So consequently, when fabricating cylindrical pressure vessels from rolled formed plates, the longitudinal joints must be designed to carry twice as much stress as the circumferential joint. So if you are going to design a vessel, no, a cylindrical vessel, okay, so the stress that will govern here obviously will be sigma 1. Okay, so we will use this, no, in designing the the a cylinder or a thin uh, vessel, no, or cylindrical vessel, no, since this will govern, no, since it will produce a maximum stress. Okay, anyway. Okay, so now let's proceed to the second type of thin-walled vessel, which is a spherical vessel. So we can analyze a spherical pressure vessel in a similar manner. To do this, consider the vessel to have a wall thickness T, inner radius R, and subjected to an internal gauge pressure P, as shown in figure 8-A. So if the vessel is sectioned in half, okay, so if you are going to section this sphere in half, now we will see this free body diagram. So take note that if we are going to cut the sphere, no, in half in any section here, no, it will have the same free body diagram, right? So like in the cylinder, equilibrium in the y direction. Okay, so the loadings here will be in y direction, so the y-axis is here. Okay, so these loadings are all in the y direction. So the pressure or the stress, okay, the stress that the wall of this spherical vessel, okay, it will be subjected with this stress. So the stress will be denoted as sigma 2 here. But here we cannot say if this is a spherical, a tangential stress or a longitudinal stress, because anywhere you cut the sphere in half, it will have the same diba? It will have the same free body diagram, and it will also have the same stress lang. No, so this stress sigma 2, no, and the pressure P, so the pressure P, this is again caused by the contained gas or liquid, no, of the spherical vessel. Okay, so we can solve the sigma 2 or the stress in the spherical vessel wall, no, by summing of forces with respect to the y-axis, since they are both in y direction. No? So this will be equal to 0. So to do that, we will convert sigma 2 into force, no, by multiplying the area where it will act, no. So the area will be the area of this of this wall. So this wall is a circle, since this is a sphere. So this is a circle, so that will just be the circumference of the inner circle, which is 2 pi r, times the thickness of the wall. So that will be 2 pi rt. And then since the pressure is opposite in direction, so that will be negative here. And then we will multiply the pressure by its area to make it a force, no? So the area, no, wherein the pressure will act will be the area of the inner wall, okay, or the inner circle here, which is pi r squared. Okay, so that will be equal to 0. So to solve for sigma 2, so we will just transpose this on the other side and then divide both sides by 2 pi RT. Okay, so to solve for sigma 2, that will just be PR over 2T. So this will now be the stress in spherical vessel wall. Okay. So this is the same as you will notice here, no? So this is the same result as that obtained for the longitudinal stress in the cylindrical pressure vessel, right? So furthermore, from the analysis, this stress will be the same regardless of the orientation of the hemispheric free body diagram. So consequently, a small element of the material is subjected to the state of stress as shown in figure 8 to A. Okay. Okay, so let's solve sample problem number 1. A cylindrical pressure vessel has an inner diameter of 4 feet and a thickness of 1/2 inch. Determine the maximum internal pressure it can sustain so that neither its circumferential nor its longitudinal stress component exceeds 20 kSI. So, under the same conditions, what is the maximum internal pressure that a similar size spherical vessel can sustain? Okay, so let's solve this problem. Okay, so we are going to solve the maximum internal pressure without exceeding 20 kSI, no, in the stress for cylindrical vessel and for spherical vessel. So we will start with the cylindrical vessel. So to solve this, no, so as we know, the maximum stress here will occur in the circumferential direction. Okay, or in short, the maximum stress here will be the tangential or circumferential stress, no? So since we know that it will have a greater value than the longitudinal stress, right? So we are going to solve for the tangential or circumferential stress, which is equal to PR over T. So we have here the given stress, which is 20 kSI. So we will use that here. And then it is also, the radius is also given in the problem, and the thickness is also given, right? So we will just substitute those values to solve for the pressure. No, so that's what we are going to solve here, the internal pressure. Okay, so this will be 20, so that's the given allowable stress, no? So 20 kips per inches squared, so that will be equal to P, and the given radius is 24 inches, and the given thickness is 1/2 inches. So solving for the internal pressure, so that will be 0.41667 KSI. Okay, so pressure will also have the same unit as stress. No, so pressure is also force over area, so that will also be KSI. Okay, so this will now be the pressure for circumferential circumferential direction. And if you are going to solve actually for the longitudinal stress, no, so substituting the value, no, the formula, so this is PR over 2T, so it will give us a pressure of 833.33 psi. Okay, so if you are going to use this pressure here, no, instead of this pressure, no, we use this 833.33 psi here. So what will happen here is that since the pressure, okay, is increased, no, this stress will also be increased, and if this stress is increased, no, it will exceed the allowable, which is 20 kSI. So we cannot use, no, the stress in the longitudinal direction. Okay, because yun nga, the maximum that the maximum pressure that the cylindrical vessel can withstand is this pressure already. So this will now be the answer for this. The pressure is 416.67 psi for cylindrical pressure vessel. Now, what if the vessel is a spherical vessel? No, so if it is a spherical vessel and we are going to solve for the stress, no? So here the maximum stress occurs in any two perpendicular directions on an element of the vessel. So it will be maximum if we cut the spherical vessel in half. Okay, so the formula for this will be equal to PR over 2T. Okay, so substituting the allowable stress, which is 20 kips per inches square, and then equal to P and the given radius or inner radius, no, that is 24 inches over 2 times the thickness, which is 1/2 inches. So the pressure here will be 0.83333 KSI or 833.33 PSI. So this will now be the answer for this. Now, take note and notice that although it is more difficult to fabricate, the spherical pressure vessel will carry twice as much internal pressure as a cylindrical vessel. Okay, so cylindrical vessels or no, spherical vessels, no, they are they can withstand greater pressure, no, compared to cylindrical vessels, no. So the downside nga is that it is more difficult, no, it is more difficult to fabricate a spherical vessel than a cylindrical vessel. That's why we can uh, see more frequently cylindrical vessels compared to spherical vessels, right? Because it is easier nga to fabricate than spherical vessels. Okay. Now let's proceed to sample problem number 2. A cylindrical steel tank has a thickness of 20 millimeter. The length of the tank is 4 meters and diameter is 1.80 meters as shown in the figure. Compute the following. Letter A, the tangential stress in the steel wall if the cylinder is completely filled with liquid whose density is 748.90 kilogram per meter cube. And for letter B, the hydrostatic pressure acting on the wall of the steel tank. Okay, so we are going to solve for the tangential stress and the pressure. Okay, so let's solve this problem. Okay, so for this problem, to solve this, no, for the tangential stress, okay, we are going to cut the cylinder this way, no, so it will be cut this way. So this will be the free body diagram of the segment, of the cut segment. Okay, now, in the given, no, there is a density of the liquid, no, that is the content of the cylinder, no, of the cylindrical vessel. So we have to solve first, no, the force, no, caused by that that liquid, no. So to solve for the force, that is equal to rho gv, wherein rho here is the density and g here is the acceleration due to gravity and v here is the volume of the cylinder. Okay, so substituting the values here, so the density of the liquid, no, that is 748.90 kilogram per meter cube, no, and then the gravity or the acceleration due to gravity is 9.81 meter per second squared times the volume of the cylinder. So the volume of the cylinder is just the volume, no, or the inner wall, the volume of the inner wall. So that is just the area of the inner circle, which is pi over 4 diameter squared, no, if it is in diameter, or pi r squared if what we're going to use is radius. So again, if it's diameter, no, the area is pi over 4 diameter squared, and then times the height of the cylinder, no. So in this case, the diameter is 1.80, no, so 1.80 meters. Okay, so the height is 4 meters. Okay, so the force here, okay, or the hydrostatic force here is equal to 74,780.39 Newton. Okay, so what we need is actually pressure, right? So the pressure that we want to solve, no, it can be solved by this formula, force over A. So the force that we computed here will be this force, and the area will be the area where that force is acting, or the pressure is acting, no. So this is the area where the force is acting or the pressure is acting. Okay, so the area of this is 1.80 meter times this height, which is 4 meters. So that's how we can solve the pressure, no? So this will become 74,780.39 Newton over the area, which is 1.80 times 4 meters. So again, class, you have to be very consistent with your units, okay, so that you will not get lost here. Okay, so the pressure here will now be 10,386.17. So the unit is Newton per meter squared or Pascal. Okay, so this is the hydrostatic pressure that we are solving here, ha? Okay, now, if we are going to solve for the tangential stress, no, in the wall, no, so this wall of of this cylinder, no, it will be subjected to a tangential stress, no, or a circumferential stress. Okay, so the formula for that is PR over T, wherein P here is the pressure, the R is the inner radius, and T here is the thickness of the wall. Okay, so substituting the pressure that we solved, that is 10,386.17 times the radius. So the radius is half of the diameter, ha? Don't get confused here. So the radius therefore will be 0.90 over the thickness, which is 0.20. No? That is the thickness of the wall. Now, the tangential stress here, if we compute it, this will become 46,737.77 Pascal. So this will now be the answer for this problem. So that concludes our discussion for this topic. I hope that you learn and attain the learning outcomes. So for additional bonus points, okay, so I would like you to comment in the comment section what you learned, okay, in our discussion about the tangential and longitudinal stress in thin-walled pressure vessel. So you just have to comment your name, your section, and the concept that you learn from that topic. Okay, so see to it also that you answered the assessment task for this topic, okay, and submit that on the following meeting. So also class, please subscribe to this channel and like and share this video. So thank you class for listening, and God bless. Bye bye. Keep safe.